Okay, so we get started again. So the second half of section 6.4.2 deals with work which is done against gravity. So the first one, it was sort of all situations in which, the formula for the force is just, this nice formula. What's going to happen in 6.4.2 situations is you're going to have to think a little bit more about how to come up with what the formula for the force is going to be. And we're going to be in situations like this. We've got a chain that's lying on the ground. And we're going to pick one end of the chain, and we're going to lift up the chain so that it is 5 meters above the ground, and the chain is going to hang directly down from it. And what's going to be complicated about these situations is not the force is going to, it's not like, it's the force due to gravity changes as you get higher. But what happens is as you get higher and higher and higher, you're lifting more and more of the chain. As you go higher up in the air, there's more and more of the chain that's actually off the ground that you're actually lifting. So different parts of the chain get lifted different distances. And that's what's going to make these sorts of questions more complicated. So that's what I'm just sort of going to mention before I move into the material for this. So the idea is what's going on in these sorts of situations, in a lot of these problems, you've got you've got a large object, and different parts of the object are moved by different distances. So in this situation, rather than the force changing, what's actually happening is the distance is changing. Right? Before it was like the work is the force times distance, and the force changes, you move over different distances. Here the distance traveled by different parts of the object is going to be different. So when we're constructing a Riemann sum to approximate the work done, rather than taking the distance traveled and dividing the distance traveled up into pieces, what we're going to do is we're going to actually take the object and cut the object up into pieces and calculate the work done on each piece of the object and turn that into an integral. So the idea is what we're going to do is if we have that situation with a chain lying on the ground, right, so we have a chain lying on the ground here. What we do is we take the length of the chain and we cut the chain up into pieces. And we look at this piece and say, okay, what's the force required to lift that piece? How high are we lifting that piece? We take this piece, say, what's the force required to lift that piece? How high are we lifting that piece? Right? What's the force required to lift this piece? How high are we lifting this piece? Etc. Because each piece is being lifted to a different height. So as we go along the chain, the heights are what are changing. So what we need to do is for each piece, we need a formula for the work done on each part. And the formula for the work done is going to depend upon two things. It's going to depend upon the location of that part, the xi star, which part are we talking about, also depend upon the length of the part. Because, of course, the longer the piece is, the heavier it is. So the more force is required to lift it. And we're going to add those amounts of work together to create a Riemann sum. Once we have a Riemann sum, we can turn it into an integral. Now here, there's not one nice integral formula that works for all these problems. Here we're going to sort of have to address each problem separately. And in each separate problem, sort of think a little bit about how can we come up with that Riemann sum formula, how do we turn the Riemann sum formula into an integral formula. And for a lot of the other applications that are coming up this week, we're going to have to do that. Each problem is going to have to be addressed individually. There's not just one integral formula we can memorize that applies to all problems. Any questions about this idea of slicing an object into pieces before we move on to examples? Okay. So first I'm going to give you a couple of physics formulas for work done against gravity. The first thing to mention is that the force due to gravity is the mass of an object times this number g, which in metric is 9.8 meters per second squared. The nice thing about g is that one of the weird nice things about imperial is an imperial g is actually just 1. G is 1 pound per pound. And the reason is because in imperial we measure force in pounds, and we also measure mass in pounds. We use the same unit for both, and that's why g turns. Whereas in metric we don't. We use force. Oh.
Mass is measured in slugs.
The mass is in kilograms.
No, but imperial is in slugs.
Sorry?
Force is pounds, but in imperial it's slugs per mass.
Oh, yes. It depends which, yes. So, yeah, in this textbook, it's always pounds and pounds. Yeah. I was going to say, you're right that if you're actually doing actual physics in imperial, it's different. In this particular textbook, they only ever use pounds for imperial mass and pounds for imperial force, which means in this particular textbook, it's 1. Again, I don't intend to give you any actual imperial questions on the test, but on the web assignment there will be some. So the key thing, of course, is the force is m times g. The work is always the force times the distance, so it's m times g times d. So when you're lifting a flexible object like a chain, different parts of the chain will be lifted different amounts, which is the idea I was talking about here. So if we want to calculate the work done with a given part, what we've got to do is you've got to calculate the mass of that part. And the formula for the mass of the part of the chain is going to involve a delta x. Right? The longer the chain is, the heavier it is. You're going to multiply this mass by g. You're going to multiply it by the distance that part has to be raised by. And that gives you the work done on that part of the chain. You can turn this formula into a Riemann sum formula and then into an integral formula. So here we have a situation where a chain lying on the ground is 10 meters long and its mass is 80 kilograms. And the question is, how much work is required to raise one end of the chain to a height of 6 meters? So the first thing to mention is that this chain is 10 meters long, right? So if we take a piece of the chain of length delta x, a piece of length delta x is delta x over 10 of the chain, right? So if delta x was 5, it would be half of the chain. It would be 5/10 of the chain. If delta x was 1, it would be 1/10 of the chain, right? So the mass here is going to be delta x over 10 times 80, right? So it's half the chain, it's going to be half of the 80 kilograms. If it's 1/10 of the chain, it's going to be 1/10 of the 80 kilograms, right? The idea is, another way of thinking about it is we can, calculate what n is, how many pieces are we dividing it into by taking delta, which are 10 over delta x, and then saying, okay, we're dividing the 80 into n pieces. That also works, but this is basically going to be the formula for the mass. Another way of thinking about it is it's 80 kilograms, it's 10 meters, so it's 8 kilograms per meter. So if the length is delta x meter, it's 8 times delta x would give you the mass. But the idea is the mass is going to depend upon how long a piece of the chain you're picking. So that's now the formula for the mass. The distance, so the first piece of the chain, the 0th piece of the chain goes up 6 meters. If we go a distance of x along the chain, this piece is going to have to be raised x meters less. It's going to be hanging x meters below the top. So this height here is going to be 6 minus x. So that means the work is going to be m, which is 8 delta x, times g, which is 9.8, times 6 minus x. And this is the work done on one piece of the chain. So one piece of the chain of length delta x, the amount is going to have to be raised by is going to be 6 minus x. The g is 9.8, and the mass is 8 times delta x. That means the total work is approximately the sum of these guys. 8 times 9.8 times 6 minus x. Delta x. So if we can approximate this thing with a Riemann sum, we can evaluate it with an integral. The integral is going to be 8 times 9.8 times 6 minus x dx. Now the other thing to mention, which I haven't mentioned so far, is what are the limits of integration here? Can anyone actually tell me what the limits of integration here are?
Depends on the length of the chain.
There's like the chain is 10 meters long.
So 0 to 10 meters?
It's actually not 0 to 10 meters because the end of the chain doesn't leave the ground. It's only 0 to 6. And you sort of have to visualize that the final situation, one end of the chain is going to be 6 meters above the ground, but this end of the chain is not actually leaving the ground. So only from 0 to 6 is actually being lifted up. If this was 5 meters long, then it would be from 0 to 5. It would be the whole chain that's being lifted up. But because the chain is longer than the height that the end is being lifted to, there's going to be 4 meters of it which are still going to be on the ground. So we're actually going to have the integral from 0 to 6 of that thing. And if we calculate that thing, 8 times 9.8, let me use a calculator. $78.4. So here's the integral we have to evaluate. So we want to evaluate this integral. I'm going to pull a 78.4 up front as a constant. The derivative of 6 minus x is 6x minus x squared over 2. This whole thing goes from 0 to 6. So we have 78.4 times 6 times 6 is 36. 6 squared over 2 is 18. Plug in 0. 6 times 0 is 0. 6 squared over 2 is 0. I'm just going to write this whole thing as a 0. So 36 minus 18 minus 0. And again, with our calculator, we can figure out what that number actually equals. By the way, if you type this sort of answer into WebAssignment, WebAssignment will usually accept this as correct. So, and usually, again, I don't really need you to do the further calculations once you've got an answer, which is a number, even if it's a really complicated number. I trust your calculators can do the rest of that for you. Any other questions about this example? Yes?
So that 6 you got from 0 to 6, if you teach your height to 7, it would be 0 to 7, right?
Yeah. Yeah. If it was raised to 11 meters, then it would actually be 0 to 10. Oh, the other thing that will change is that this number will change. Right? If it's height to 7, this will be 7. If it's height to 11, this will be 11. But if it's going up to 11 meters, it'll still only be integrating from 0 to 10 because you'll hit the end of the chain after you get to 10. That's the idea, right? After 10 meters, there'll be nothing left to lift up.
What would happen to the extra 1 meter that you're lifting? Wouldn't there still be work being done?
There's still work being done, and that's being counted here.
Okay.
Being calculated, that's because you're still lifting it higher.
Okay.
That's the idea, because this number would change from 10 to 11, but this number would not.
Right.
Yeah. Yeah, these numbers here are representing the pieces of the chain. This number here is representing how high you're lifting it. They're different things. Yeah. Any other questions about this? Okay. I'm going to do a couple examples of the harder problems which are like this. And the harder problems are like this are ones that involve pumping liquids. And the reason they're harder is because they're three-dimensional. The principles are the same as the principles here. The only difference is rather than dealing with like a chain, which just has one dimension, you have to deal with like a tank full of liquid. So if we want to calculate, for example, how much work is done in emptying a tank of water, or how much work is done if you want to siphon someone's gas, like those sorts of. Actually, no work is, now that I think about it, no work is done if you're siphoning because you put it down below the level of the tank and it flows out. But anyways, so if you want to you use this idea to calculate the amount of work required to drain liquid out of a tank. What you've got to do is you've got to take this tank and you've got to slice up that tank into horizontal slices. And for each horizontal slice, you've got to calculate the mass of that slice. You've got to calculate the distance you have to raise that slice, and use that to calculate the work done. So here we have a swimming pool. It's in the shape of a circle. It's got a diameter of 24 feet. It's got a depth of 5 feet, or it's 5 feet high. And the water level is at 4 feet. And here I want you to set up an integral to determine how much work is required to pump all the water out over the side. Here I don't care about evaluating the integral, I just want you to set it up. Again, here, when they're talking about water, they use pounds to measure the density of water. So the key thing, so the idea here is we're going to cut this piece of water into slices like this. So I'm just going to draw a slice in red. A slice is going to look like that red thing there. Bring slices out of that tank of water at different heights. Now the height we're going to measure along the y-axis, it's a vertical thing. So I'm going to measure the length of that slice as delta y, right? So the mass is always the density times the volume. The density here is 62.5. That's what it says on the slide there. The water weighs 62 pounds per cubic foot. Now the volume of this thing is a cylinder. If you want to calculate this volume, you want to calculate the area of the circle on top times the width. So it's going to be pi r squared times the h here is delta y. So it's 62.5 pi. Now the radius of this thing is half of the diameter. So 12 squared delta y. So that's now the formula for the mass. The mass is 62.5 pi times 12 squared delta y. Now, the other thing we need to calculate is how high do we have to raise this piece of thing, this slice of the water? Well, we have to raise it up to the top of the tank. So if we're taking the slice at a height of y, we've got to raise it up to here, to height of 5. So the distance is going to be 5 minus y. It's going to be the height we have to raise it to minus the height it's at. So the work is going to be, mgd. M is 62.5 pi times 144 delta y. G here is 1 because we're working at imperial, we're measuring mass in pounds, which again is technically not a unit of mass, but for like ordinary cases we consider it to be a unit of mass. And the d here is 5 minus y. That's the formula for the work done to raise this slice up and over the sides of this pool. So, here's the work done to raise one slice. So if we want to calculate the total work, we're going to have to take a Riemann sum of this thing. Just to make this formula simpler, I'm going to multiply the 144 by the 62.5, which gives you 9,000 pi 5 minus y delta y. This is going to be the formula for the total work done. This is the formula for the total work done. We can churn that Riemann sum into an integral. 9,000 pi 5 minus y dy. One thing to mention here, I'm actually just going to mention this now because I realized I've been doing this. In a lot of the other examples, I kept writing yi star up until this point and then switched to y when I switched from a sum sign to an integral sign. Here I'm just writing y both times, and the reason is just to save space on the board, not having to write the I and the star. Basically, the height of this slice is really a sample point in the middle of the slice, right? We're either picking the top of the slice to measure the height, or the bottom of the slice, or the middle. And that's what sort of the I star represents, is it's either the right endpoint, left endpoint, or midpoint. Here I'm sort of ignoring that. I'm not dealing with it because it was not going to make a difference, whether picking top, middle, bottom, or middle. I'm sort of just calling it y rather than yi star. But if that's confusing you, the difference between y and yi star, they're basically the same thing, is the short answer. But, okay. Now the other thing to mention is, again, we didn't find our limits of integration. Well, the first slice we're taking at the bottom of the tank. The way I've measured my y-axis, that's y equals 0. Last slice, I'm taking at a height of 4 feet. So the limits of integration here are going to be from 0 to 4. And now here I said set up but do not evaluate an integral, so we can stop here. We don't need to actually go any farther than this. We've set up the integral. We can use a computer or whatever to actually do the integration for us. Yes?
So
I'm assuming this isn't the intention of the question, but when you're pumping water out of a pool, isn't all the water being pumped up the full 5 feet because you're always taking water out of the bottom of the pool?
Yes and no. What happens is actually when you put the hose in the pool, the water actually fills up the hose to this height. If you put a hose in a pool, the water will actually flow up the hose to this height just due to gravity. And so the first piece of water you're only picking up from this height. And then when this water level gets lower, then you have to pick it up from the next height. Once the water level gets lower, then you have to pick it up from the next height. Because as your pool's draining, the water level in the hose you're pumping it out of is also draining. That's the idea. Yes,
Would
Dylan.
there not be an extra amount of work to move the water out of the pool more than
Like-
lifting it up?
Horizontally, yes. So there is sort of they're glossing over the fact that there is. Now, the amount of work required to move it sideways is only existing because there's friction on the inside of the hose. So we're ignoring things like friction. Otherwise, when you move it sideways, you're actually doing work to start moving sideways, and you're regaining that energy when it starts to go over the edge and fall back down again.
Okay.
So practically speaking, it's not significant, but yes, technically speaking, if this was if this was an engineering situation rather than a math situation, you'd have to worry about that sort of stuff. Because this is a math problem, I'm only really talking about the amount of work that's done against gravity. The amount that's work, yeah. That's the only part I'm actually worried about, but yes, in an engineering situation, there would be other types of work as well. Anyone else have any questions? Great. So the last example in this section is example 6. So here we have a half-full spherical tank of oil. The radius is 3 meters, and the pipe is 1 meter above the top of the tank. So here we have a spherical tank. The oil is here in the middle of the tank. We try to pump it up that way through a pipe that's 1 meter above the top of the tank. So this distance up top is 1 meter. The radius of this tank is 3 meters. And the density of the oil is 900 kilograms per meter cubed. So, the first thing we're going to do again is sort of consider, let's say we took a slice like that. It's supposed to be circular. Let's say we took a slice like that of a liquid. What we need to measure is what's the mass of this slice and what's the distance we're going to have to raise that slice. So the first thing to measure is when we're measuring the mass of the slice. The mass is going to be the density, which is 900, times the volume of that thing. And the volume of that thing is going to be pi r squared h. Right? It's a cylinder. So the volume is going to be pi times the radius squared, because it's the area of a circle, times the thickness of this cylinder. Now the thickness here again is just delta y. So again, I'm going to put my y-axis with 0 at the bottom of the tank. And the height y is measuring how high up the tank I've gone. Now what's going to be difficult here is that the radius of this thing is going to change depending upon how high up you take the slice. At the bottom of the tank, the radius is very small. It's almost 0. Up in the middle of the tank, the radius is 3 meters. So as we go up, that radius is changing. And so I'm just going to draw another picture. So here's the center of a circle. This distance is y. The distance up from the bottom where we're taking a slice, that distance is y. This distance is r. That's what we want to measure. And if we draw a line like that, that distance is 3. 3 meters. That's sort of the center of the tank to the edge of the tank. So, since that is y, this distance is 3 minus y. And then, hey, look, we can use the Pythagorean theorem. R squared is 3 squared minus 3 minus y squared. So r is the square root of 9 minus 3 minus y squared. And again, I don't have to put the plus or minus because radius is length, it's always going to be a positive number. So now I can take this and I can put it into the formula. So the mass of this thing is going to be 900 times pi times square root 9 minus 3 minus y squared. Oh, sorry, the squared. Yes, squared there. And then put another squared out here. And the h here is delta y. So now that's my formula for the mass of that slice. The other thing I need to measure is the distance I need to raise the slice. Well, this thing is at height y. Up here, the place I'm going to have to raise it to is going to be height 7. Because the middle of the tank is height 3, top of the tank is height 6. 1 meter above the top is height 7. So the distance is going to be 7 minus y. So the work done on one slice, work due to gravity, is going to be the mass, which is 900 pi 9 minus 3 minus y squared. Basically, the square and the square root are going to cancel itself out. Delta y times g, which is 9.8. I'm running out of space. Okay. I'm going to have to rewrite that and take up a little less space and a lot more space on the edge of the board. So, 900 pi 9 minus 3 minus y squared, delta y, g, which is 9.8, times 7 minus y. The mass times g times the height we have to raise it. So the total work is the sum of these things. I'm just going to do the 900 times 9.8 on my calculator. 8820 pi 9 minus 3 minus y squared 7 minus y delta y. And if we want to turn this into an integral, total work's approximately this sum, so the work is actually the integral of 8820 pi 9 minus 3 minus y squared, oops, the squared's in the wrong place now, 7 minus y dy, and the limits of integration here are going to be from, you're going to start measuring at the bottom of the tank, you're going to stop measuring when you get to the water level, from 0 to 3. Now, this is an integral that's complicated enough, I would not ask you to actually evaluate this, I would just ask you to set up the integral, but do not evaluate it. A lot of these problems are situations like that, where this is like a, you could do it, it's just ugly, and it's not worth sort of going through the work to do this when we have computers that can do this faster. So, by the way, at some point I may, depends how the course is going, I may sort of show you how to actually do integrals using computers, because again, they're faster and more reliable than we are to do these sorts of things, and again, the more important skill is not, being able to do the integrals yourself, but being able to know what to actually type into the computer. Be able to know what sort of integral I actually need to type in order to calculate this thing. Okay. Yes?
What are these 7 minus y again?
The 7 minus y? Well, here, this is at height y. I've got to pump it up to the top here. The distance I need to pump it is from height y to height 7. Now, why is this 7? Because this is 3, this is 3, this is 1. 3 plus 3 plus 1 is 7. Yeah. So you have... Any other questions? Okay. I'm not going to start Chapter 8 today because we only have 20 minutes left. If I start Chapter 8, there won't be any time for group problems. So I'm going to give you folks the group problems. Again, the material, these applications are getting a little bit sort of requiring more conceptual thinking. One of the things to mention of these sorts of problems is on the test, I will likely not ask you to evaluate any of these integrals just to set them up. With volume problems, area problems, I'm more likely to actually ask you to evaluate them. These ones I'll probably just say write out the integral. And a lot of these, and test questions will likely be a little bit easier, like a little bit less complicated formula-wise than these ones here. But yeah, the book doesn't have a very good selection of ones that aren't too complicated. So the group problems here are these two. Oh, that's supposed to be pounds, not foot. This is supposed to be the LB, foot pounds. How much work does it need to stretch at 9 inches beyond its natural length? So these are both work questions. Take a look at them, work on with your groups on them. And again, you've got about 15 minutes, 10 or 15 minutes to work on them, and then I'll go over the answers. Here are some of these point cards, if you want to take some, fill them in. I'll give you a hint to start off with, is that the first problem uses this formula for a spring. F equals kx, yeah. That will be on a formula sheet on your test. So again, it's not on the slide, it's on the handout, but yeah. You'll need this to start with at least. These are both imperial questions. I don't know how that. Anyways.